So let's get all of that in place here. Now, one of the things that happens, of course, is that because we had a lot of space to set all this up, we're now out of space. So I've got to do like in those big lecture halls where you lift the boards, right? I've got to lift all this stuff up for the next slide. So that's the lift up right there. There's that thing that we had before, so you can compare and see the stuff at the bottom is now sitting right here. So this is the equation for this pseudo-velocity. The velocity has an extra translation added to it. Now the translation itself is complex. Like everything here, this one comes to be imaginary, okay, with that epsilon. But the epsilon is complex, so that it is a complex number sitting in practically every spot there. Okay, so here's what we got to work on. Right now, here's the key thing. Remember, I said that when you have an e to the I bt, well, when you have e to the I angle, you're doing a rotation on this complex number, right? E to the minus I bt, which is the one that you always get in the hammer, that's always left-handed, right? So we're talking about phasor now, right? Remember we talked about phasor? Well, here I'm just saying I'm going to do a rotation of this velocity vector. That's going to be my solution, really, up to this crossed electric and magnetic field problem. Okay, and with a minus sign, it's a clockwise, left-handed, 2D rotation. Everything's 2D here, x and y. Okay, so this is what we get from that. We get that the v is 0, and we remember that the v 0 is the old velocity, little v, plus that translation that we've added. And remember, we're keeping the electric field and the magnetic field constant, so this is something that you're adding a constant to a dynamic quantity. Okay? And another way to write it. So once we get this done, this is the complex form, then we're going to translate it back to the real form. The real form is a matrix form. Okay? What we're seeing here is the velocity is equal to a rotation by the b of the big V, and the big V has got this extra translation on. You have to be sure to add them with a y here and a minus sign and an x here. That's what the complex numbers are telling you. And then the electric field is just straight off a switch to the y. This time it's plus because I got a minus sign there, and then the x comes down with the minus sign not changing. So there it is. That's the solution for the velocity. We still have to integrate that. But we'll integrate this instead of that, or you can do it either way. At this point, we're really close to having a really nice geometrical solution to crossed B and E field motion. We need a coordinate. You actually get the coordinate now. Okay, so do an integral of that guy right there. Get some extra factors. Okay, and get this constant, have a t on it, and then have an integration constant left over. And we can actually calculate that as well. So this is the complex form to the coordinate solution that comes out of this thing. And here it is being written out explicitly at the very bottom line of this page. Yeah, they're all the same now. Okay? So here is our x coordinate and our y coordinate. Now, of course, it'd be nice to just write that as a matrix too, just to make things again, I'm going to take my board and lift it, okay, here, both of these, all three of them actually, and this is where we stand right now. There's the complex form for the coordinate x plus iy, and now it's just a question of making some sense out of that, this is a rotation of something right here that involves initial conditions of the velocity and the electric field. This one just the electric field, but it's times time. And then here's the just the static initial positions of this thing, and you have to have that in order to get started with the motion that comes from x and y as a function of time. So let's let this one up too. And now we're going to start drawing some pictures of this that make some geometrical sense. And this is something which I won't go, in order to avoid missing out on all of the demos that go with this lecture, I'm going to skirt through this. And this is where you would check your right-hand rule to see that it's happening. But the basic thing that I'm going to put in the center board here is, once again, we're going to have a generalized cycloid. That is, we're going to have a wheel that rolls on a highway like the wheel that the stick had after it got punched. And then there was a center of percussion of radius. That's going to be the radius of an actual, and this wheel is like the wheel you see on a railroad car, right? It has a flange, right? The flange is the thing that's making the curling cycloid. If I can adjust these parameters here, I can get a pure cycloid by just somehow reducing the rim to the radius of the wheel. Okay, so the basic idea of having a wheel with a rim, and the thing that I'm referring to with the rim is RW. That turns out to be E over B squared, and the rest of it is pretty easy to see after you've played with. So something that you kind of have to do yourself in order now, given a problem on this particular E cross B field motion, and I'm asking you to go ahead and plot a few of these cycloids, both the curlate ones, but also some interesting prolate ones, which we'll see as we get to play with this some more. Okay, so you're going to get curves kind of like that. This is drawn by an old program. We have a brand new program that's working really well that TC's built out of the old one. It's called Coulout, C-O-U-L, because it mostly is dealing with Coulomb fields, but not exclusively. You can deal with other things. And this is the control panel that goes with that. And I will just briefly show that, just to give you an idea of what is involved with it. I think I might do it on the center screen. And let me get the last screen here up, not that one, keep that one where it is. This one up to speed. Now, you can see on the left-hand side there are a lot of things that you can change. We're doing a Stark versus Zeeman field. That's the name the physicists give to electric fields and to magnetic fields respectively. But with this particular one, what I'm going to do right away, before we get into the fancy stuff, is I'm going to get rid of the check here for plotting this, what we call the swarm. This thing right here, do swarm, okay, I'm going to uncheck that. Basically, you'll see what that does, is it puts out a whole bunch of particles like we did when we had the volcanoes of Io, right? We had a bunch of trajectories go out. We're going to do the same thing here. That's really beautiful. But let's just do one, just to see what's the basic properties of these things. And I'm going to make the number of burst paths equal to 1. That means one trajectory like that. And then, of course, you can set the initial conditions, but the best way to do that is just to click on the screen once the animation is working. And I'm going to try to make it work right now. Let's just get it going here. Okay. And there's a typical cycloid. It goes up there, infinite curvature, and then infinite curvature with the opposite sign. That's what's going on in the little peaks there. Okay. And to have that right now it's just doing one particle out of the swarm, but what I want to do here is I want to go ahead and turn the swarm off. And I also want to turn the electric field off for the time being. So I'm going to go get the electric field here.
One more
That's
down.
the Z field right here. Okay, I think the best way to get rid of that for sure is to do a 0, right? Okay, so that gets that to happen. And then I should be free to set my initial conditions out here. Now I have a B field of 1. Okay, and that's kind of what is on your problem. I just took units to make things easy here. But I'm just going to go here and plot something with a velocity, say, this way. Okay, that's the way you set the momentum. And what do I get? I get a phasor. Oh, wow. Another phasor. Okay, these trajectories are nothing but phasors without the electric field, right? No matter where I go, and you've probably seen pictures of bubble chambers, which have a bunch of little circles. These are their spirals because there's loss. We don't have any friction here. But basically, that's all this thing can do in a magnetic field, is just go around in a clockwise circle. No matter where you start, no matter how you throw it, I can throw it up, and it'll go around that circle. I can throw it down, it'll go around that circle. You see? No matter where I go, it just makes a circle out of everything. That's all you get. Okay? All right, that's kind of neat. Now, what I want to do now is go ahead and turn that electric field on, and I forget what it was that was before I turned it off. This guy right here.
One up. You're real close. There you are.
And I forget what the number was. I could look it up right here, I think, electric field 0.1 with a minus sign. So what this could be, and that's what it is in your problem, could be gravity. Okay, gravity's down, so we're going to put a minus 0.1 on the electric field. We're going to let that be the driving force. I mean, how does this thing know? It is the mass working on it. So I'm going to try to make the electric field be minus 0.1. It means I have to get a little closer to the center there. And I probably ought to just go and click this number right here. We still don't have the best of all controls for numbers that you could have, but there's where I have the field that we've got. Now when I click on this
You shifted the
thing...
Zeeman accidentally.
Pardon?
You shifted the Zeeman field accidentally.
Oh dear.
Something dragged across it. And
Okay, let me get rid of the...
that's the 1.
I want to have that be plus 1. Right. Okay. Let me... I'm pushing on the wrong computer here. Okay. There. That should be what we got. And where's my start field? What happened to it?
You're still good. One more down, you can see it.
That's it. Minus 0.1 in the Y direction. Okay. So I start off here. I get my cycloid. Okay. Now that's all I can make. And it's getting kind of cluttered here. So let's go ahead and bring the thing down where I can erase paths. Let's start over. Okay. So this time I'm going to throw the particle a little bit to the left. Okay. And that's what I want you to find, or close to that. This is gravity, and this is what the particle does. It never falls. Well, it falls a little bit and hops back up again. If I was really perfect with that number that I put in there for velocity, I could make the thing go a straight line. Okay, so that's a really simple trajectory that this thing does. Okay. If I throw it the other way, like this, I get curly Q. I still follow the line at some points, right? And no matter where I throw the thing, I still intersect with that thing at a particular place. Okay? So at this point, it's worthwhile studying the swarms. Okay? And so I'm going to go back down here and turn on the swarm. And then the question is, how many particles do I want to have? I'm going to have a 24, okay? So I just click here. Isn't that beautiful? So these are the things you can make with this. Can't do that with that thing down there. But this is what's going on. And if the swarm is really tight, and I color it according to Lagrangian, I get the wave functions for E cross B. Okay, that's something you should remember from this course. That's the semi-classical way that Rick Heller talks about. Okay? All right. I think we've said enough. It's about time for us to hurry up a little bit here, or we're going to be way over time. And so what I'm going to do is take us back to the lecture. And there's a pretty good example of what we can make with the thing. We just did something like that. But here's the mechanical analog. And I'm going to sort of zoom through this thing a little bit, but what we're dealing with here is a ball rolling on a table and not slipping. That's the hard part, is to get some lucite that's really clean, a billiard ball that's really round, and not have any dust particles. Every time there's a dust particle, it bounces, it slips a little bit. So we have, trying to make something really ideal here, and we're going to be turning this thing at a certain rate, and that rate is going to be the B field. That's going to determine the B field and the A field. The A field actually is in the plane, as we've already mentioned, this thing is doing. So let's get all of this thing. Now, at some point, probably going to just have to run the movie to see it, and then we can, if you want to stick around and play with the actual machine, you're welcome to do that. It's a lot of fun. And I think maybe somebody figure out an easy way to make a cheap one of those. It would be a neat game billiards is fun just with a flat stationary table, but something like this, oh boy. Anyway, what we have to do in order to take the equations of motion here and the basic idea of no slipping condition is this. This is just straight on Gibbs type notation. We're talking about the translational force that has mass times velocity. We're talking about here the rotational torque that this thing is getting, F cross R, okay, and that is proportional to omega dot, omega being up there, vertically up to this thing. So omega cross R is part of the velocity. That's really what makes this thing move. But what you can see here, the mechanics of this thing is in some ways more complicated than the mechanics of the actual field that it's representing. And I'm just going to put all of these things here together so you can see what it finally comes out to be. This is a mechanical cyclotron, as I said a couple of times already. Now what's neat is that this coefficient of the acceleration, and then here is B cross V. Remember, the omega is the thing that represents the actual B vector coming up through the thing, and having its vector potential be perpendicular to that, so that the curl of that comes out to be a constant. And so what you get is 1 plus the inertia that you'd be associated with if this thing was just a hoop of radius r, but the actual inertia of a ball is 2/5 mr squared. So we get 1 plus 1 over 2/5. That comes out to be 7/2. And that's the bottom line on this device right there. Now go ahead and put it on this screen here. But let's see it in motion. So this is the thing that we want to compare. If it's a solid ball, and that's what we've got on the table there, and will be in the video, this inertia over mr squared is 2/5. Well, that makes this right here, the actual cyclotron frequency, to be 2/7 of omega. Well, that just means that this table, which has a little white mark on it, it's right there, that's got to go around 2 times for every 7 times the ball goes around its trajectory. That's what that is saying. That, I mean, it's like, you know, it's a geared analog, but the ball is just doing what a ball does when it rotates on the table. So, without further ado, we play the movie. And you count the ball when I say 0. 1, 2, 3, 4, 5, 6, 7. It should have gone around twice. That's the thing to check when you play with this particular video here. Lots of other videos to play with. This is on YouTube, and then you get some ads with it. But you know, this is cool. Now you notice that the circle has gotten a little bigger. That's because it's little imperfections in the ball and the table that are causing it to you know, do that. I will simply back out of this thing here, but come back to it right now and then pause. Okay, so that is what one thing I want to show you. We only have a couple more minutes here. I do want to show you the very end of this thing, the punchline to this particular situation with the pool hall setting their bumpers. Okay, and the idea is that if the center of percussion, that's this, is above where it's making a contact, then when it hits, it's going to kick this way. It's going to slide, and you don't want that. That messes up a bumper shot. All right? A good pool table will adjust that big H just so that it matches. And it can't be the other way either. That is, if your center of percussion, that magic radius of P, is now when it hits, the ball's going to skid this way. You don't want any skidding. You want it to rotate around this point when it hits that. Isn't that cool? I mean, that's, you wouldn't think there'd be all that much physics at the local pool hall, but if it's a reputable house of ill repute, it will have done this calculation. So that's the important thing that I wanted you to see. Okay, the rest of this will just be start this thing up and see if it will actually do it for the real thing. And I've got it pretty well balanced here. Now, one of the things that you can do with this, and we're going to do it later when we talk about resonance in the cyclotron, is I can tip the table this way or that way, and that's like putting an electric field in this direction, either this direction or that direction. Okay. Anyway, let's see what we can get going here. I'm going to crank it up to about 40. That's not 40 miles an hour, but it's 40 on this dial here. And I'm going to grab this ball, which is doing what it's supposed to do, but I'm going to put it in the center here, give it a little kick. And that's a cyclotron orbit. And actually, I can control where it's headed by putting the electric field a little bit to bring it back toward me, toward you. Okay, by doing that. Now it's doing a curlate cycloid. Coming toward you. I turn it the other way, I can maybe, before it goes off the edge, catch it and make it go the other way. Okay, I've got to tip it. So the electric field makes it. And you can hear it sort of catching on something, like a little dust particle makes a sound, even though you can't see it. But if I bring this thing up to a fair speed here, it's surprising how well it'll hang on even though it's and then what's called parametric resonance is when I wiggle the field. That's something we'll talk about later on too. That's the modern way to do cyclotron resonance. There, it hit something that really made a sound. At some point, the static friction is going to break. That's it. Okay, the proton came out and, whew, I've got radiation poisoning. Okay, so anyway, this is something you can fool around with. I mean, in any time you want to. It doesn't have to be a pool ball. Actually, I find tennis ball isn't too bad, but it slips very quickly and gets the ball back into the. I planned that. Okay. Anyway, that gives you some feeling, and it doesn't matter that the ball is a different size. I meant to pull out a ball bearing here that I had. I don't know what happened to it. Got a whole bunch of balls. It's also fun to, at a reasonable speed, go ahead and put 2 of them on here and give one of them a little different velocity and see if they run into each other. But the little ball, if it's solid, will have the same frequency, 2 to 7. There, now they're dancing. They're all dancing the same music. A little bit of perturbations from collisions. That's what I was trying to get them to kiss. They don't stay kissed, but sometimes it takes a while before they. I still can't find that ball bearing. I'll try this one. This should be the same. Whoop! Got hit right away.
Oh, it's a champ.
Center.
He's still dancing, right? They're in step.
But this one's 2 to 7 as well.
There's still.
Bring the electric field that way, and it starts to bring it out. Now, if you can make a cheap one of these, people will buy it. I mean, they bought the Newton's balls, they ought to buy these balls, right? Now I've got one left. Anyway, come up and fool around with it. We'll bring it up again when we talk about resonance, because there's where you see the phase and all that kind of stuff, playing a role in getting energy into the cyclotron.